Right, welcome. Thank you for joining us. I will bringing the training that I promised, and for a long time I couldn't because of a busy schedule. But thank God today we are starting it, and I will be bringing training on the design of a staircase, a special type of staircase known as open well staircase. And this staircase, though we have some softwares that can design most of this staircase for us, but most of the times we find ourselves in a situation where we don't have a software readily available. So how do you do when you are faced or you are challenged by a design? You have a design to make, but you don't have a software to use. What comes to your mind? What is the solution? Now we are trying to provide some solution. So in this training I will be showing us how we can apply our knowledge of Excel in developing an open well staircase. A staircase are template that we will use to design a real life staircase. It's like we'll be using a good example and a good textbook, and our is super simple and super easy. Let me give you a brief what you are expecting to see. This is what I've developed and I've used it for some time. Now this is this, and in my own way of developing software, I like separating the input from the output, where these represent the input and this other side represents the output where you could print for as your design report or design brief or for documentation or for referrals, as the case may be. So stay tuned. Without wasting much time, let's get started. Okay, I've already pre-designed the template for us where we will use because of time, because designing all these things will take much of our time. Our design will be to BS8110, reinforced design of concrete, and our resource material is from engineer Victor Yonega's reinforced concrete design textbook, the abstract of design of staircase. From that textbook we are going to see how we can automate using that. He is in Dr. Oyenoga has been one of the great minds and the authorities that we have in structural engineering, and his books has helped a lot of people, including me, during university days and even during practice. A lot of people still use his books, so you can reach out to him and get one of his books. His books are very, very interesting. Now today we want to look at open well staircase, and we hope it's going to be a two-part training. You like and subscribe to our page so that we'll be bringing most of this training so that you get notification as often as possible, while we are trying our best to make sure that we simplify the strains related to engineering design and so on. One of the things we want to do will be to put in some parameters, and as an engineer I believe you have already known most of the parameters. For example, we want to use 24 the characteristic strength of concrete and steel 410, what is obtainable in the market. The going of the staircase is 300 while the riser will be 150, and we are going to use a live load of 1.5 for residential, assuming this is a residential building, and a finished load of 1.2, and we are going to calculate the steps later. Let's put other parameters. And the waist of the staircase, we are going to link it up. We don't want you to put the waist as it is. We want to use a drop down, so I'm going to expand this for now. I've already put this for waist. This is the bar diameter and also the space. We come to data. How do you use data validation? And then we come to list. From list we select this range, alright, and click enter. There's other ways we can also do that, which if you are familiar with Excel you should know that. Okay, this one is the width of the staircase. From there is 1500. It will show us in the textbook when we go. This is the width of the staircase, 15. This 15, 15, 15, the width of the stairs. Okay, let's continue. Diameter of still the same thing. We are still going to use data validation. From data to list. From list we click on resource and click on the link. Okay, already is there, so we can select it 12. Here the waist we can select, let's say 120, and the cover we can put 25, depending on the level of what fire resistance you want to provide for the building. That will go in line with the slab cover. The beam width is 230, and okay, now the diameter of steel for flight 1, we have, this is flight 1, this is flight 2, and this is flight 3. So we are designing it differently. So we want to put the steel diameter for flight 1 in. Now here will be no need for me to, okay, let me do it once again, but others I will copy. From data validation, click select on list. From list, resources. From resources, click on this, and then okay. So this validation is enter. Let's select 12. Number of steps, let's look at the one we have here. For the first flight 1, we have 1, 2, 3, 4, 5. We have 5 steps. The width of first landing is 1.5. 1.5 is it? 1.5. So width of first landing 1500 millimeter, and the spacing will be the same thing. From data validation, list resources, click on this. Okay, click on OK. Now that's the spacing. So you can use 120 starting from 100, and use 100 or whichever one, depending on what your design will say. We are just putting those things so that we see. Another thing we want to put is a diameter of steel for flight 3. Why do we have to design flight 3 before flight 2? If you are familiar with the open well staircase, you know that flight 2 depends on flight 3 and flight 1, and it is the most critical flight of open well staircase. So if you consult the code, you will know better. So let's keep on. I'm going to copy this to minimize our time, and then the number of steps in that one is what? Let's look at it. Number of steps in flight 3 is 1, 2, 3, 4, 5, 6, 7, 8. There are 8. There are 8 steps, and the landing is up to 1.5, 1500, and the spacing will still be the same thing. We copy here and put for data validation. Okay. Now we go to the second flight. Diameter of still the same thing, so we are going to copy. Okay. Number of steps. What is the number of steps there? The number of steps 1, 2, 3, 4 is going to be 4. So let's put 4. While the third landing is 1500, same thing. Most buildings, the landings are always the same in special cases where the architect is struggling with space, but most buildings have the same landing. The spacing is going to be the same, so we are going to copy this and paste. And flight 2 being the critical flight, we have to design even the west of the slab as it is. So I'm going to copy this one that we've already put west. It's going to be from the same axis. So I'm going to paste it there. Okay, and that is it for now. Now let's come back. We are good to go to start our calculations. But the first thing to do is to calculate self weight, which is what? 0.5. Let's look at from this. This is self weight of steps. 0.5 times 150. This 0.15 is the risers, while 24 is the characteristic strength of concrete. So we are going to put that equals to 0.5 times, going to open bracket, this is the riser, divided by 1000 because in meters. It's in millimeters, so we have to convert it to meters, times the characteristic strength of concrete. We click OK, so it gives us 1.8. Now that is done. After this, when we finish, we are going to log that particular cell. You won't be able to edit it. Only when you change the value to change, because it's going to be linked here. And if you come to this if we now come to the output, this is how we are through with our input, where we'll be playing along with those values to get the desired product. So we want to look at the own weight of what? Look at this is example of our staircase, own weight of the west of the staircase. So we want to look at it. So what is the own weight? Equals to the same thing we do for steps. The self weight, that will be what? The self weight will be the weight of the waist of the slab, like divided by 1000 times the strength of concrete. Okay. While finishes is just for us to link finishes. Steps is for us to link the steps, and live load is for us to link the live load. This will take time and do it. Why slope factor? Slope factor from the slope factor, this is the formula. This formula is like using Pythagoras theorem on the steps. Using Pythagoras theorem, then divide it by the landing to get the slope factor. I'm using Pythagoras theorem on this. The height times this square plus this square, the square root of that divided by this. So that is what we are going to do. That will be equals to what? The square root. There's a function called square root, SQRT. The square root of what? The square root of this square plus this square. Okay, divided by this. Now the next thing is for us to do is the load factor, the factored load F. Now factored load, how do we calculate it? Let's still look at the code. How do we calculate factored load? This is the factored load. F equals to what is 3.6? 3.6 is what? 3.6 is concrete only, that is for the west, plus 1.2, that is the 1.2 is the finishes, times what? The load factor. You multiply the sum of those with the load factor, then you add the steps, okay? Plus times the factor for dead load, because that is the dead load. Now we now look at what? The life load times the factor for the life load. So let's see how we can put that. This will be equals to, we open a bracket, open it again. We are saying that is what? This plus this, close the bracket, times what? The slope factor, we close the bracket again, times what? The factor of load for the dead load, the factor for dead load, okay? After this is going to be plus the step on weight, before we now multiply it by the factored load. Close it, open this one to make it complete. Then we now open for the life load. Life load is what? This times the factor. And what is the factor? This is the factor for life load, 1.6. So enter. Let us do that again. We enter, this is the own weight, that is for the west, this plus the finishes times the load factor plus the own weight of steps multiplied by the load factor for dead load plus the life load multiplied by the factor of life load. Okay, we are through with the factored load. Now let's look at the span. What is the span for span 1? We have the steps, the sum of the steps plus half of the landing. So what is going to be will be, and how do we get it? How many steps do we have? For us to calculate this place, it's going to be what? This times the landing, the going, right, going or landing, plus what? This divided by 2. So that gives us that. Okay, you can still put it in brackets so that we don't mix up, but Excel will calculate that correctly for us. Okay, that is in millimeter. Divide all of them by 1 meter or 1000 to get it to meter. I have to convert it to meters. Okay, so we are going to divide it by 1000. Now give us in meter 2.25. Now the moment there is, this is the moment for span 1. That is 1 over, that is FL square, FL1 square over 8. 1 over 8 is 0.125. So this is like saying FL square over 8. So we are going to enter it. This is what? 0.125 multiply by the factored load multiply by the length square, that is the moment, 7.155 kilonewton per meter as we run. Now the next thing is effective depth. Effective depth is equals to what? Is the weight of the slab minus cover minus half the diameter. So since we are in flight 1, we are going to use this divided by 2. Okay, so if we change this to 150, it will increase. Okay, so that's the factor that defines it. Now the width is, since we are designing staircase, it's like slab, we are designing staircase per meter run, so we are using it 1 meter as the width of the staircase. Then K factor is when we will now deploy this formula. Now this is the formula. K equals to what? M over BD square FCK, right? So now let's input it. This equals to what? M, this M times 10 raised to power of 6. Why is it times 10 raised to power of 6? Because this is what? Kilonewton per meter, and our width is in millimeter. So the kilo now raised to power 3, and the meter, to convert to meter to millimeter, multiply by around 1000. That makes it 10 raised to power 6. Okay, divided by, open bracket. Please take note of what I'm doing here. because if I don't put bracket, it's going to assume a different thing. I will show us what it will be. Let us enter the correct thing first. The b here is this times the d is what? This times this. That is a d square, or we can say this raised to power of 2 times FCK is the characteristic strength of concrete, which is what? This. We close the bracket and enter. Now that is the K factor 0. This. Let me copy this formula and show us why we have to. Now you see this one. Now I'm going to remove this bracket on the division so that you see. Have you seen the answer? It's quite different. You see the difference now. So if I didn't include this bracket, it would have been a different thing. So that is why one has to be careful while entering formulas. Okay. Now the next one will be Z, the lever arm. Lever arm is d times what? This is the square root of this. This raised to power, of course, we know from indices that raised to power have a square root. So that is what we are going to enter. So what we do, we are going to leave d alone and then enter 0.5 from 0.5 of what? So this will be equals to open bracket 0.5 plus we open another bracket, or we can write square root here, but let me write it this way. Later I will write with square root so that we can see how it is. Open another bracket, that is 0.25, and then minus, we open another bracket, minus what is our K over 0.9. We close the bracket again, and then raised to power of open bracket 1 over 2 or 0.5, and we enter. So ask us to close the bracket. Okay, so 0.75. Okay, so if we multiply by d, now times, okay, d times, let's put d in the front. What is our d? Effective depth, and we now put times to now give us a reasonable value. Okay, now the next thing will be for us to find the area of steel required. Now, so this is the formula for AS required. AS required equals M over 0.95 FYZ. Okay, so let's enter. Equals to, our M is what? This. Remember, open bracket, our M is this times 10 raised to power of 6. I've explained why it is so. Okay, divided by what? 0.95 times, we're supposed to open a bracket, so let's open bracket there, so that, of course, I've explained that, times Fy is characteristic strength of steel, so this is it. Okay, times the Z, which is this, and close the bracket and enter. The area of steel required is 179. Let's find the area of steel provided before we proceed. This will be equals to what? We know that steel is always circular, so we are going to use pi, the area of steel, pi times d square over 4 equals to this. We have to do it in respect to the spacing. To find it is going to be, I'm going to put this in bracket, multiply it by 1000, then divide it by the spacing. That is how to find the area of steel provided. So this is the area of steel provided with 12 millimeter with 100 spacing. If we increase the spacing, it's going to reduce. So we can now say, okay, let's increase the spacing to 150. It will still pass. Okay, because this is the area of steel required, this is the area of steel provided. That's okay. Now the next thing will be for us to enter the provision. Okay, so this will be what? Equals to, we can combine text and a cell value. We can make reference to a cell value at the same time combine it with text to produce a write-up. What am I saying? Look at this. This is a combination. Let me show this. This is what I'm saying. Let me reduce this to 4. Now it said provide Y12 at 150. If I reduce this to, let's say, 175, it will change to 175. If I change this to, let's say, 10, it will change to 10. And the area as well reflects. Understand? So that is what we are going to do. So now what we are going to do will be equals to, we open it to write a text, to call out a text in your formula, you have to put it inside double quotation. So this will be what? Provide what? Close it. Provide what? Y, close it. And to combine it, we use and, that symbol, and. We provide what? We provide this, Y12, and at, we combine it again, at this, that's the spacing, okay. We combine it again, open bracket, millimeter, that's the spacing, millimeter. We have to put center to center, bottom, we open bracket and combine it again. What is the area? This is the area, okay. And then we combine it again. Please, you can take time and say, I'm going to explain this. Combine it again and close the bracket. Okay, before we close the bracket, I will put what? That is millimeter square, and I will close the bracket and close it. Okay, let's look at what is happening. Okay, this one is supposed to be down here. Okay, now what is this showing? You see this area? Now provide Y12 at 200 meters, center to center, bottom this. Now the reason why this is showing that, let me put this, round this up, round up. There's supposed to be a parenthesis there. Okay, the same thing is happening here. Let's round this up in case it's in this thing. Round up, because use parameter there, okay. Now we are providing Y12 at 200 center to center, bottom. The area is what? 566 millimeter square. If I reduce this, you see it change. If I increase this, let's say to 16, it will also change. Alright, so we are providing Y16 at 175 millimeter center to center. Okay, so that is working perfectly. Let's reduce this to this and maybe increase this to where it was before. Okay, now that we are through with, okay, the next thing is for us to do flight 3. Let's look at flight 3. Flight 3, look at this. We have a step plus half landing here. So we have to be taking care of that. So the span will be equals to what? We will put what? Flight 3 Ds times what? The going plus open bracket, flight 3 width of landing divided by 2, close bracket, plus open bracket again, flight 2 width of landing, because this is the width of landing. This is the width of landing of flight 2. This is what of flight 3. So we are going to still divide it by 2, close the bracket and enter. That is the span for. Then I'm going to divide all of them by 1 meter, converting it to meter. Divide all of them by 1,000. That convert it to meter. So this meter. Now the next thing will be for us to put moment. What is that moment? The moment is what? What was the formula we used for the moment? Formula moment is what? FL square over 8. Okay. Moment is FL square over 8. So we are going to say equals to 0.125 times our span, our load times our span square, span 2 square. So we enter. That is our moment 23.639. Okay, we want to look at effective depth. Effective depth is the same thing as this one, so we are going to copy it. And what was it? Let's put it. This is equals to what? The width, the waist of the slab, minus the cover, minus diameter of span flight 3 divided by 2 as effective depth, and our width is still 1 meter. We are divided by meter run, and the curve factor still remains the same, which before we copy anything, if there is a cell that will remain constant, we have to lock that cell. So this one, the cell that will remain constant is this. So this is what? E7. So we are pressing F4. When you click anywhere near E7, press F4, it will lock it. We click on enter. So we can now copy it. That will fix that particular reference. Okay. So that is it. The same thing with lever arm. We are going to copy it. You can still go through the formula. The lever arm is not linked to any other thing. Still within the distance. So we are copying it. Okay. Let's look at it. Okay. And the next thing is the area provided. It links to E8, which is the strength of steel. So we have to lock that one by pressing F4 to lock it, so we can still copy it. The reason why we are copying is to make work easier for us. Click on enter. Okay. Now the next one will be for us to this one as well. Going to adopt a different method of copying. This one will be here, and I will change the address. The spacing will be to this one, like 3, and the diameter will be to this one. Not change the address by dragging and dropping. So if you change this, it's supposed to work. Okay, it works perfectly. If you change this, it's supposed to work. Alright, it's working perfectly. Now what we need to do is to still do the same thing here. I'm going to copy this. There are different ways of copying. If you just select and copy, it will, as you move it, whether you move it up or down, it will also move the reference up. If you are moving it up, if you are moving it down, it will move the reference cells down as well. But if you select and highlight from the formula bar and copy, the cells remain the same. Like what I'm doing, also select formula bar and paste. Now you see the reference remains the same. Now I can now change the reference. This is the spacing. This is spacing for flight 2, and this is the area of steel provided. So I can now click on OK. The diameter of steel also needs to be changed. So this one also change. So I can now play along with this. So if this is 12, okay, and if this is okay, everything is working perfectly. Now we can now go to the second flight. Now we are through with flight 1 and flight 2. We will now go to the second flight design, because that is the most critical flight, and we reserve that for the last. So follow us and see how that will be done. Now the first thing is the span. What is the span? The span of flight 2. The span of flight 2 is equals to what? Combining the first landing, the second landing, and the number of steps inside. So what we first do will be the number of steps times the number of steps times that plus flight 3 landing and flight 2, because flight 1 and flight 2 landing. So this will be flight 1 landing. Where is flight 1 landing? This plus flight 3 landing. Flight 2 landing, and enter. So this is the effective span for flight 2. So the next thing we have to do is to find the total load, total unload. This one has to do with total unload, because if you look at this, at this point, there is part of this load is coming here, part of this load is coming here. So it's going to be a little bit tricky. So let's look at what is obtainable here. Let's see what happened here. Now we have flight 1, flight 2, we are through with that. We are doing flight 3 now. After we compare these parameters and see what is happening, whether we have the right thing. Okay. Now we want to look at flight 3, total unload. This total unload is the factored load times the width of the stays times the length of the stays. The length, that is the span of the second flight. So what do we do? And this span is minus. Remember, when you're talking about the span, you have to consider the beam. the beam, and let us go there. Now we know it's going to be beam here, and the width of that beam has been defined here. That beam has been defined here. So it will be half here, which in turn will remove the total beam. Because when you remove half here, half of 230, half of 230, it will become a full beam. So you have to remove that to get the effective width of or unload of that particular stage. So in that case, what we are having here will be, what we are having here is 4.1 minus 230. That will give us what? That is 4.3235 minus 230. That is half of that distance will give us 4.1. So let us see how we can automate that here. This will be equal to what? The factored load times the width of the stage, which is 1.5, and we have to divide it by, convert it to meters. Please, the unit must be consistent. Convert it to meters times the load, the span, and before I put the span, let me put it in bracket because I'm going to do some modification there. The span minus the beam. Where is the beam? Beam width, close bracket, divided by 1000 to convert it to meters, and click enter. So this is the effective total unload of that span, total unload of this particular span, the unload of this. Okay. Now the next thing we want to calculate is from flight 1. What is the load that is coming from flight 1? Flight 1, total unload of this divided by 5. Okay, divided by 2. Alright. What is it? It's going to be equals to the factored load times the width. What is the width of span 1? This divided by 100. Close it, times what? The length span 1, that is span 1, times 0.5. Okay, we enter. Now that has given us for the second span. Okay, now let's look at this flight from flight 1. 1.5 is the width. Okay, this is 1.3. What was the span for flight 1? This is flight 1. 2 plus this. Now the load we are using for flight 1 is not the total this thing. We are not considering plus 75. You know, this is this times this plus. We are not considering the load from the landing. We are only considering the load from the steps. So we are going to modify that. We are considering the load from the steps. So now the span now will be what? We are going to change this particular one. We are not going to make reference to this entirely. So what we are going to do will be what? Will be, what we are doing will be 5 times this divided by 1000. Close the bracket. This will be inside the bracket. We are modifying the load from 1. We are not considering the load from the landing when we are putting the unload from this. That is why it has reduced. That one was very high. It has reduced. What are we saying? If you look at this is, we are using 1.375. 1.375 is 5 times 275, excluding 75. 75 is half of 1.5. Okay, that's 750, half of 1.5. Okay. Now, load for flight 2, the same thing. We are not going to consider the load from we're not going to consider from the landing, but we are going to consider just from the state. So we are going to do the same thing, equals to this times, I will open bracket, flight 2, flight 3, load for flight 3, 8 times this divided by 1000 to convert it to meters, and then times what? 0.5. Okay, this times this. Okay, we've not included the width. Let's thus multiply with the width. The width is what? Width of span 3 this divided by 1000 and enter. Okay, we are through with the load for flight 3. Okay, now will be the what? Total load, the 1.5 meter. Okay, the 1.5 meter width. So we are going to sum all of these. Total load per meter equals to summing this, not including the length. Okay, now per meter run, that will be equals to what? This divided by 1.5. We are going to change that later. Okay, but it will be this divided, because we are talking about the 1.5, that is the width of the stage. That is why it is 1.5 meter run. So this divided by 1000, close the bracket. Okay, so this one is that. So now the moment, what will be the moment? The moment for flight 3. What is the moment for flight 3? Let's look at it again. Moment for flight 3 is 0.1 times FL square, 0.1. I multiply it by 1. The moment will be equals to 0.10 times total load times the length square. This square. Enter. I'm going to change this to meter. Okay, if I'm doing that, I need to put this in bracket. But let's see. Others has been in meter, so let's change this to meter. I'm going to divide it by 1000. Divided by 1000 and change the unit to meter. Okay, and this is the moment. Now the effective depth will remain the same. So what I'm going to do will be effective depth. I'm going to copy. Okay, let's enter it. Equals to the width, slab width minus spacing, that's minus cover, minus diameter for flight 3, diameter for flight 3 divided by 2, effective depth. The width is still 1 meter. The factor the same thing, and the lever arm should be the same thing. We are going to look at it because there is some modification. K factor has to do with effective depth and this. Okay, BD square FCK. I already love the FCK. Okay, the moment. Alright, while this is the moment and the K factor should be moment, lever arm moment and the K factor. Okay, and the area of seal required, I'm still going to copy it. Alright, let's look at it. The moment and the lever arm. Okay, that worked perfectly, and let's also copy this and look at the values. This is supposed to be the stirrup and the spacing. And what else again? Okay, those are the two references. Alright, now we are going to copy this as well. Now let's look at this. This will be the reinforcement, the spacing, reinforcement and spacing. Let's look at this area again. No, this one again is not the west, is the spacing. Okay, and this. Okay, now that we are through with that, let's double check this. Remind this so I can have a better view. I want to check this 16. Okay, it changes, and 150. Okay, it's changed. Let's say Why are we having negative value as total unload? Let's look at this formula. Like after span, the total unload is what? Okay, I later changed this to, it was in millimeter, I changed it to meter. That's what affected this. So let us do, is going to be, we're going to divide the width of the beam by 1 meter. I have to change some placement of, okay, it has gone back to what it was before. Okay, I've been able to rectify that. And the next thing is lever arm. Now let's rectify this. We've noticed this number, it shows that something is wrong. When you input this formula, the lever arm, when you input this formula, this particular part is a square root, and there is no square root of a negative number. That is why it's flat curve. What you have is minus 0.2, because when you say k over 9 is this, and m minus 0.25 minus this is minus 0.29. So it's negative, that's why it's flat curve this error. So the issue is we have looked into the formula for the moment. This is the moment here, is the moment per meter run, which is this, times the span times 1.2, that is 1 over 8. That's F over 8. Okay, so we are going to rectify that now from this moment. So there is no square. I will clarify that later with the code to know what we are doing, and we'll come back to clarify. Now everything has returned to normal because we have put that now 1.25 times the span times the length. Okay, now everything has returned to normal, so we can move ahead.
Thank you. This is where we'll be ending today because of time. Since we have designed the all 3 flight 1, 2, 3, and we have seen those parameters, the values, how it is being provided. Next time will be for us to do some design checks, that is like shear and then deflection. We know that in structural design of members, especially slab, that which a slab family where staircase belong, their deflection is very important, very important, because if the building pass in other thing but fails in deflection, that means the slab is also failed. It might lead to disaster. So checking is very important. So that will be our concentration next time. And apart from that, we are going to add some additional features to fine-tune our workbook to look professional, as such that we can at least click and print. So thank you and stay tuned. Make sure you like and subscribe to our Facebook. Comment a way we can improve it. This training is for us, and I need your feedback. Make sure you comment at the comment section, whether in our social media as you are following us, and like and share. Thank you and God bless.